Hello and welcome to the Chemistry Academy. In this video we're going to go over National 5 Redox reactions. So if you're studying National 5 Chemistry, this will benefit you in Unit 3, but also if you're crashing higher chemistry, this will be useful for you to watch before you start Redox reactions in the Unit 1 of higher. And also just if you've done National 5 Chemistry and you now moved on to higher, just for a little refresher. So if we get started, the main thing to remember when it comes to redox reactions, so there are two separate reactions that always happen at the same time. So redox is just like a word of reduction and oxidation. So you guys are maybe too young to remember this, but when Brad Pitt and Angelina Jolie got together, we called them Brangelina. That's essentially what we've done here with reduction and oxidation reactions. So when it comes to National 5 level redox reactions, it's all about whether things are gaining or losing electrons in the reaction. So, like I said, both reactions always happen at the same time, which means when one thing gains electrons, another thing is losing them. And that's why the electron transfer can actually happen, because one thing's there to give electrons away to the other thing that's going to gain them. To remember which way round it is, we always use this mnemonic oil rig. So that stands for oxidation is loss of electrons and reduction is gain of electrons. So if you just remember oil rig, that'll help you remember which way around it is. Oxidation is loss of electrons, reduction is gain of electrons. If you then go to the back of your data booklet where you'll find the Electrochemical series, that has got a list of reduction reactions. So it does say at the top reduction reactions or something to do with reduction. So that is there as a reminder that from left to right, those reactions are reductions. If you need to write an oxidation reaction, all you need to do is write the reaction back to front, so from right to left. And that's because oxidation is just the opposite of reduction. So if your reduction reaction going from left to right is a reduction, then writing this one backwards would be an oxidation. So if I had the Ag solid here, I'll just write it down. So if this is the reduction reaction shown in the data booklet and I want the oxidation, I just write it back to front. So AgS, then the arrow, then the Ag plus the 1 electron, and that would be the oxidation version. Okay? So, looking at these two examples of reduction and oxidation I've got here, we can tell this is an oxidation reaction because electrons are being given off. They're on the product side. So that means they're being lost. In this reaction here, the electrons are being taken on, they're being gained, they're a reactant, therefore that makes this a reduction. You can sometimes double check in the electrochemical series to see if the reaction you're given is reduction or oxidation. You can just see which direction it's going in on the electrochemical series. So if the equation you're shown in the exam is exactly written in the electrochemical series in the correct order, then that would indicate to you it's a reduction reaction. If you see the reaction but it's back to front, then that shows that the one you've been given in the exam is an oxidation. So, but in my opinion, it's better to understand what's actually going on. So if the electrons are being given off, that's them being lost, so it's oxidation. If they're being taken on and they're a reactant, then that would be reduction because they're being gained. So that's the two separate what we call half equations or ion-electron half equations that are going on. We can then be asked to write the overall redox reaction equation. So like I said, both these oxidation and reduction reactions happen at the same time. So we can write an overall equation to show what's going on. In order to do this, it's a bit like simultaneous equations in maths. What we need to do is get the electrons to cancel out. So if I take a different colour of pen. So we've got 2 electrons in this equation and only 1 in this equation, which means we're going to times this bottom equation through by 2. So when we do that, we have to multiply everything in the equation by 2. So we need to times this by 2, this by 2, and this by 2. Now you can see that we've got 2 electrons in each of the equations. That means we can then cancel these out because they are the same. And then everything else we're left with just gets mushed together and written on the same line. So it's sometimes a good idea when you're starting off doing this to put like a line through your arrows so you can see which side each things are on. So if I draw my chemical reaction line, we've got 2Cl minus on the right hand side plus 2Ag plus, and then on the product side we've got Cl2 as a gas and then the 2 silver as a solid, and then that's all we've got. So that would be our overall redox reaction. So in order to write those, all you need to do is get the electrons to cancel out and then mush everything together. My advice would be is to write down what you're going to multiply the equation by next to the equation, because sometimes you can forget, especially if you're multiplying both, have to multiply both of the reactions. We'll get to an example like that in a second. It just keeps you right and reminds you what you're multiplying through by on each of the reactions. Okay, so main things to remember so far: oxidation is loss of electrons, reduction is gain of electrons, and to write the overall redox equation you need to get the electrons to be the same number and then they can cancel out and you just mush everything together. The other thing I wanted to highlight here, because this does catch a lot of people out in the exams when it's asked, if you're extracting a metal from its ore, if you're not sure what I mean by that, then go and watch my video on metals and metal extraction. But metals are found in ores, which are compounds we find naturally in the environment. But in order to use metals, we need to extract them. When the metals are extracted from their ores, it's a reduction reaction that's happening to the metal ions. So the metal ions are reduced into metal atoms. Okay? So quite often you will get asked what type of reactions are occurring when metals are extracted. It's always reduction. They're always reduced. So that's just something I wanted to highlight to remember. But we'll go and do a more complicated example of the balancing redox equations, and then we'll move on to electrochemical cells. Okay, so we've got another set of reduction and oxidation reactions here. And this time our oxidation reaction involves the magnesium solid going to magnesium ions. We can tell it's oxidation because electrons are being given off, they're being lost. And then our reduction reaction is iron 3 accepting 3 electrons to become iron solid. And again, we can tell this is a reduction reaction because the electrons are being gained by the iron ions and it's becoming iron atoms. So in order to write the overall redox reaction here, we need again to get the electrons to cancel. So this is probably the hardest sort of example you'll get. We've got 2 electrons here, 3 electrons here. So there's nothing we can multiply to, no whole numbers we can multiply 2 by to get to 3, which means we have to multiply both equations essentially by each other. So we have to times this top one by 3 and the bottom one by 2. Okay, because if we times this by 3 it'll give us 6 and this by 2 would give us 6. So we multiply again the whole equation through by these numbers that we've decided to multiply by. So if I multiply all this by 3, and this is where having your multiplier written down helps because it stops you getting confused. And then this one's getting multiplied through by 2. Okay, every time I go to multiply something I double check what my multiplier is. Now that our electrons are both 6, they can get cancelled out and everything gets written on the same line. So again, if you get confused and sometimes put stuff on the wrong side, draw your squiggly line through the arrows. And then on the left we've got 3 Mg solid plus 2 Fe3 plus Aq going to 3 Mg2 plus Aq plus 2 Fe solid, and that's our overall redox equation. So like I said, that's probably the hardest example you would get, where you're having to multiply both equations to get the electrons to cancel, but it's really not that complicated, to be honest. It's probably one of the easier marked in the National 5 paper, really. Okay, so what we'll move on to now is electrochemical cells, which is where we use these redox reactions to create electricity. If you're studying higher and just looking for a refresher, you probably don't need to watch the rest of this video because the electrochemical cells is not taken forward into higher. So yeah, all you really need to know is identifying oxidation reduction reactions and how to write an overall balanced redox equation. So if you fall into the I'm doing higher chemistry now boat, then thanks very much and I'll see you soon. But if you're doing National 5, hang on because we're about to go into the electrochemical cells. Okay, National 5ers, so now we're going to look at the electrochemical cells. So what I've done here is laid out diagrams of the 3 different types of electrochemical cells you will come across. They're basically all the same thing because they all produce electricity and an electrical current by causing a flow of electrons. However, the way they're set up and the substances that are in them is a little bit different, so we'll go through them. But yes, essentially an electrochemical cell is just chemists using metals and non-metals that will gain and lose electrons in order to create a flow of electrons, which is essentially an electrical current, so you will get electricity. So if we were to put a bulb in the middle of here, it would light up, or you might have seen in school teacher showing you like a clock when they put it in like potato or lemon, it will light up with the time. So if we start off with a simple cell, it's essentially just 2 different metals in what we call an electrolyte solution. So you'll need to remember this term, electrolyte solution. And an electrolyte solution is essentially just any ionic solution that will conduct electricity. So sodium chloride solution is a good example of that, or it'll really just be any sort of salt solution, really, copper chloride, copper sulfate, etc. So the electrolyte solution is just an ionic solution that will conduct electricity, so it completes the circuit. In this cell we've got magnesium electrode and a copper electrode, and what you can often be asked is to identify the direction of electron flow and where those electrons would go. Now, the thing to remember when it comes to electron flow direction is electrons flow from high to low. So what we do is look up the electrochemical series. Oh, it's 1111, make a wish. Look up the electrochemical series, and the metal higher in the series will give electrons to the metal lower in the series. So magnesium is higher up than copper, which means the electrons are going to go from magnesium to copper. Now, the electrons always go through the wires. Okay, so quite often in the exam you'll be asked to draw on a diagram of a cell the path and direction of electron flow. So what you need to do in that case is on the wires draw arrows going from the metal that's higher in the series to the metal lower in the series. So in this case I'd be drawing them going from magnesium in the direction of copper. Okay, and that's essentially it for the simple cell. In terms of changing the metals, we'll talk about that when we look at the half cell diagram, because I've got the voltmeter on there. But essentially everything we're talking about and all the different types of cells would apply to the simple cell as well. It's just the only difference is it's just in one beaker. So if we then move on to the 2 half cells, so this is where you've got 2 separate beakers. Each beaker contains a different metal. To complete the circuit in this case, we have what we call an ion bridge. So this is usually just a piece of filter paper soaked in an electrolyte ionic solution, and that allows for the ions to pass from beaker to beaker. Movement of ions can also cause electricity or conductivity. You learned that when you did bonding and structure, hopefully. So the electrons don't cross over this ion bridge, it's just the ions that do, which is why we call it the ion bridge. Sometimes you can see it being called a salt bridge as well, but that's just again because the filter paper is soaked in a salt solution normally. So if you're asked in the exam what's the purpose of the ion bridge, you just say it completes the circuit. You could be asked to name what it's called as well. So again, ion bridge or salt bridge. This time though, I've got different metals. I've got zinc and copper in here. So again, for the path and direction of electron flow, they'd be going from high to low, which again would be from zinc to copper, because zinc is higher in the electrochemical series than copper is. And again, the electrons go through the wires. Anyone that's mad into physics would probably know that you actually can't get electrons flowing through a voltmeter because apparently the resistance is too high, but apparently the chemists that write the chemistry exams don't care or know about this. So just put that bit of physics info to the side if you knew that already. And this is what the FT want you to draw, so don't worry about it. When it comes to, sometimes you can be asked to complete these diagrams labelling what's in the beakers, and they'll have given you solutions or chemicals that are involved in the cell. You just basically need to take the chemicals they've given you and put them on the diagram. But what you need to remember for in this instance is then that the metals will go in a solution of their own ions. So zinc would go in a zinc ion solution, so like zinc sulfate, zinc chloride, zinc oxide, and then copper would go in a copper ion solution. So in this case I've just picked sulfate solutions, but that other ion can be different. But yeah, so just remember the metals will go in a solution of their own ions. So if you see that there's a zinc electrode and there's a zinc solution, then they would go together. Copper electrode would go with copper solution that you're given. Okay. When it comes to voltage and changing the metals, so if we were to compare these two cells in terms of which gave us the highest voltage, we would find that the magnesium copper cell gave a higher voltage than the zinc copper cell. The reason for this is because there's a bigger gap between magnesium and copper in the electrochemical series than there is between zinc and copper. So if you were to look up the electrochemical series, magnesium's all the way up here and copper's here, whereas zinc and copper are closer together. So that would be the lower voltage. So the bigger the gap in the metals within the electrochemical series, the higher the voltage of your cell will be. So that's just what you need to remember. If you're asked about voltage, you just need to look at how far apart the metals are in the electrochemical series, and the further apart, the higher the voltage will be. If you're trying to compare voltages or work out which metal's which, you need to always keep one metal the same. So we would keep, say, copper the same and then just change the other metals. That makes it a fair experiment. Because if you're changing both the metals, it's harder to pick out an actual pattern. So if you get an open-ended question on identifying metals, you can use electrochemical cells as part of your answer, because the voltage can indicate to you which metal you've got. But again, like I said, if you are doing that as the experiment, you need to keep one of the metals the same. So say we had 4 different metals, we didn't know which one was which, we could put them in a electrochemical cell with copper, and the one that gave the highest voltage with the copper would be the one highest in the electrochemical series. The one that gave the lowest voltage with the copper would be the one lowest in the electrochemical series. One other thing I will say here though is if you have 2 of the same metals, you will get 0 voltage. So if this was copper and copper, the voltage would be 0, because there's no difference in reduction potential, as we call it. So there's no reason for one of the coppers to give electrons to the other copper, and there needs to be a difference in reduction potential in order for the electrons to actually flow. Okay, if we then move on to the non-metal cells, so in the non-metal cells, what happens here is there are carbon graphite electrodes, so there's no metal electrodes in this instance. Carbon graphite, you'll quite often get asked why it can be used or why it's suitable for use as an electrode, and that's because it can conduct electricity. So carbon in the form of graphite is the only non-metal substance that can conduct electricity, as far as you know at National 5. And higher you'll learn that water can also, but I think generally we know that water can conduct electricity, but as far as National 5 chemistry goes, we only talk about carbon graphite being the only non-metal substance that can conduct electricity. So you use carbon graphite electrodes, and then in the beakers you'll have different solutions. So I've put the chemical formulas here instead because you'll quite often see them in the exam. So this is where your name and chemical knowledge comes into play. So this is iron 3 chloride, and this is potassium iodide solution. You know it's a solution because it's got the AQ state symbol next to it. Again, it's got the ion bridge, which will complete the circuit. And then quite often in the non-metal cell questions, you're given the reactions that are happening in each beaker. You could then be asked to, on the diagram, add the path and direction of electron flow. It's a bit harder with these because in the electrochemical series, the iodine isn't like named on the list. You'll find the equation there with just the chemical symbols, but it's not named. So the high to low thing's a bit harder to work out. So my advice would be in the non-metal cells where you're given the equations, just look at the equations and identify if it's reduction or oxidation. So in beaker A, we can see electrons are being gained, which means that that is reduction, because reduction is gain of electrons. In beaker B, electrons are being given off, they're being produced, they're being lost, so that would be oxidation. Okay, this then tells us that the beaker with the iodine, or the iodide, is giving electrons away, they're being lost, to the iron 3 beaker. So in terms of the path and direction of electron flow this time, the iodide beaker is losing electrons to the iron 3 beaker. So they would go in that direction from right to left, again through the wires. Okay, so the equations are given to you for the ion electron half equations are given to you. Use them to work out the path and direction of electron flow, especially if it is in a non-metal based cell, because it is a bit harder to do. Okay, the only other thing I should have mentioned, when it comes to the metal electrodes will disintegrate after a while. This is why batteries don't last forever, and they will eventually run out until you either recharge them or replace the metals. And the metal electrode that's giving electrons away will disintegrate, whereas the other electrode will actually get bigger because you're producing the solid copper when it picks up the electrons. So the copper 2 ions in this solution will pick up electrons and become copper solid, whereas the solid zinc electrode will give away electrons and become zinc ions and go into the solution. So if we were to leave this cell running for like a day, if we were then to come back at the end of the day, dry off the electrodes and weigh them, we would find that the zinc electrode had lost weight or lost mass, and the copper electrode would have gained mass, just because of the way that the redox reactions are working. Okay, so that's just another thing to bear in mind, that the metal electrodes will lose or gain mass depending on what reaction is happening to them. Okay, so that's essentially all the essential knowledge for redox reactions and electrochemical cells for National 5. So I hope you found this useful. If you did, please give it a like. Don't forget to subscribe, and I'll see you again soon.